So today's lecture is going to be on convex sets and convex functions. If you took a look at the course website, then you'd see that there's kind of different blocks of lectures on different topics throughout the semester. This first block is kind of a fundamentals block. So we're trying to learn the fundamentals of convex analysis. Essentially, it's going to prepare us for all the optimization techniques we learn and study throughout the course. So these next two lectures are, in many ways pretty basic. We're going to talk about the basic properties of convex sets and convex functions. Some people don't find this as exciting as learning a new algorithm, but we're going to see this is an extremely useful topic. So once you really understand this, it's going to open the door to kind of just looking at a function in the future and saying, that's convex. Without having to check the definition, we're going to learn a bunch of ways to do that efficiently. And it's a skill that you can develop. So that's one of the things we're trying to teach in this course. We're going to assume that you know and are comfortable with the following topics on the next two lectures and really throughout the course. And like I said, these are part of the kind of informal prereqs. Basic real analysis. So this is like continuity, differentiability of a function, what it means for a set to be open and closed, this kind of stuff. Basic real analysis. Basic multivariable calculus. So differentiability in more than one dimension, right? Gradients. Gradients of a function or the function's Hessian, which is the first or second derivative, right, of a function that goes from Euclidean space to R. And basic linear algebra. So maybe the linear algebra will soon is a little more advanced than the other two topics, but should be again familiar to you guys. If you're having trouble with the kind of prereq material, then on the course website we have some very good supplementary materials to look at. So in particular for the linear algebra material, you can take a look at these supplementary lecture videos that were made by Zico Coulter, a faculty member here in CS. They're really good. There's about, I guess maybe 10 supplementary videos that you can watch on linear algebra that cover everything from, like matrix vector multiplication, pretty basic, all the way to the, an eigendecomposition or a singular value decomposition of a matrix, which you should all be familiar with. So that's linked in the course website. Aditya Ramdas, who's a PhD student in ML, he's also made a bunch of very nice supplementary videos, kind of in the same style, for real analysis and multivariable calc. That's also linked from the course website. So take a look at all that stuff if you're having trouble. Finally, your Che Nicole made a prereq sheet that summarizes kind of more specifically through the lens of optimization what we're looking for. Okay, so there's some very good materials there. I think the prereq sheet isn't up yet. Is that right?
I have it.
Oh, okay. So it'll go up right after lecture. So you'll be able to see that. Are there any questions before we start lecture at all? Can be about material from last time, can be administrative stuff. Yeah.
So the online quiz will start, when is it? I don't remember. Is it like midnight, like the deadline is at midnight?
Right. So the online quiz, you didn't have to do the one that was for the first lecture. We did that together in class. But every lecture starting now, the quiz will be released within minutes of class finishing, and then it's due by midnight.
Oh, on the same day.
On the same day. Yeah, so we'll send out a reminder email the first few times that you have a quiz today, take it. But after that, you should remember that every lecture, right, easy quiz, like 8 questions long. Basically, it's released as soon as lecture ends, due at midnight. Any other questions? So while we're on the topic of assignments, homework 1 will go out this week. And it's due, I think it's due, don't know the exact date, January 28th, I think? 29th. So that's Thursday, 2 weeks from tomorrow. So make sure to take a look at that. We're going to try to have one homework on each block of lectures. So that homework will cover this first block of kind of fundamentals, theoretical fundamentals. And the project proposal, we'll give you information about that fairly soon. It's really not the first step of the project is a milestone where you have to turn in a proposal. It's very kind of light in terms of the amount of work required, 2 to 3 pages. So don't worry about that. We'll give you information on that soon. But you should start, if you're enrolled for the 12-unit option, you should start talking to people about finding a project partner. Okay, so we're encouraging you to work in groups of 2 or 3. So start talking to some people about that. If you're having trouble finding a partner, you can use Piazza. I think there's a forum for discussion there. You can also come and talk to one of us. All right, so let's start with the lecture. So last time we talked about kind of motivation for the course. And we ended with this idea that convexity was a very important property of an optimization problem, whether it was convex or not. And why was that true? Well, to simply put it, it's because we can broadly understand and solve convex optimization problems. That doesn't mean that it's always efficient to solve them. We'll see that it actually can be very challenging, right? Especially for large-scale problems, but for other reasons as well. But at least we can kind of broadly understand and give recipes for how to solve them. Non-convex problems are mostly treated on a case-by-case basis. So instead of being able to write down an algorithm that solves a wide class of non-convex problems, usually we just are able to figure out how to do it in a clever way for particular instances of non-convex problems. Understanding them is also a lot harder in terms of understanding the properties of their solutions, not even just finding them. Understanding the properties of their solutions is also a lot harder. So just a quick reminder, convex optimization problem, right, is of the form minimize some function f. The variable here is x. Overall value is x in some domain D. Subject to a bunch of constraints. We can have inequality constraints that look like gi of x is less than or equal to 0 for a bunch of i's, and hj of x is equal to 0 for a bunch of j's. D is the common domain of all these functions, right? And what makes this convex is if f and gi, all the inequality constraint functions, are all convex functions. And all these equality constraint functions, hj, are affine, which means that one of those guys, like hj, looks like aj transpose x plus bj for constants aj and bj. Okay, just a reminder. A very special property that we actually proved last time together, which wasn't hard, was that for any convex problem, so anything that falls into this form, any local minimizer of the problem is automatically global. So if we have something that minimizes the criterion function in any ball around itself, where that ball includes any points that are feasible, which means that they are in the domain of the optimization problem and they satisfy all the constraints, then that property, just being optimal in the local sense, implies global optimality. It's very important. So the picture was something like if we are ever at a point where we can't go downhill any further, then we know that we're done for a convex problem.
Index of j, is it 1 to r or 1 to p? Because in the equation is 1 to r and then...
Thanks. Yeah, it's just a typo. R and P are supposed to be referencing the same thing. So just that's the number of equality constraints. Any other questions? All right, so here's today's lecture. We're going to talk about convex sets. We already defined them last time, but we'll kind of talk in more depth about them. We'll give some canonical examples of convex sets, some of their key properties, and then this one is very important, this next one. And I mean, all these topics are important, but this is the one that I think if you had to remember something in particular, you should remember the operations that preserve convexity. Because this is the thing that you'll use probably the most often after this lecture. Which means that if you know a bunch of examples of convex sets, so I guess you have to remember that too, right? Some simple ones, and you see another convex set, you can recognize that second convex set as some operation of more basic convex sets. And if you know those operations preserve convexity, then you know that that new convex set is convex without having to actually check the definition. Then we're going to do the same thing, right? Definition, examples, properties, and operations that preserve convexity for functions. So arguably functions are even more important than sets because we probably use them more often in a sense of an optimization problem. But sets are more fundamental because as you'll see, everything we talk about for convex functions can be derived from convex sets. So it's really kind of a special case of the stuff we know for convex sets. So what's a convex set? We talked about this last time, just to remind you the definition. It's a set that has the property that if I have any 2 points in the set, x and y, the set being C, then that applies that the line segment joining x and y is in the set C entirely. So if I take any constant t between 0 and 1, and I look at tx plus 1 minus ty, then that has to lie in the set if x and y are in the set. It's the definition of convexity. So here's this picture, right? We saw the same picture last time. This set's not convex because the line segment leaves the set at some point. This set is convex because if I take any 2 points, x and y, and I look at the line segment between them, it's contained in the set. It's a very basic property of a set. What's a convex combination of points? So suppose I have k points in Rn. A convex combination of them is any linear combination of the points. So it has to look like theta 1 x1 plus dot 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 theta k xk. But these weights are very special in the linear combination. They have the property that they're non-negative, and they sum to 1. Okay, so that's written down here. Theta I bigger than or equal to 0, and the sum of the theta i's is equal to 1. So if you have any such linear combination, it's called a convex combination of points. The convex hull of a set, which we denote by conv C, is the set of all convex combinations of its elements. So just to be a little more explicit, the convex hull of a set C is the set of all theta 1 x1 plus theta k xk, such that k is just some, right, it's some natural number. So I can take any number of points in that convex combination. These thetas have the property that they're all non-negative and they sum to 1. And each of these points x is in the set C. So that's what we call the convex hull. It has the property that it's always convex. Okay, it doesn't matter what points I take, it's always convex. So the convex hull of any set is convex. That you can check directly from the definition. Let's just talk our way through it. Suppose I had 2 points in the convex hull. What does the line segment joining those 2 points look like? Well, I know each of those points can be represented like this, right? So if I had a point x, which was, say, the sum of theta 1 x1 through theta k xk, and I had a point y, which was the sum of, I don't know, call it, c1 y1 through cm ym, both of them being convex combinations of points in the set, then tx plus 1 minus ty is going to look like a convex combination of points again after I just move the t through, say, this sum. So t times x looks like t theta 1 x1 plus dot 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 t theta k xk, right? And the same thing with y. Then you can just directly check that those weights in the big linear combination are all non-negative, right? Because t times any of these is going to be non-negative, and they definitely sum to 1 because we know that these sum to 1, the weights on y sum to 1, and they're just multiplied by t and 1 minus t. Okay, so write that out on a piece of paper if you didn't follow it, but I just kind of talked through the fact that a convex hull of any points is definitely a convex set. So what are some examples of convex sets? Important to remember these things because, like I said, later we're going to talk about operations that preserve convexity. So it's helpful to have some basic ones in mind. There are some trivial ones like the empty set is convex, right? It's clearly convex because the statement says that if I have any 2 points in the set, then something happens. But there are no points in the set. So that statement's vacuously true, right? Well, it doesn't matter what I claim about what should happen to those 2 points. I don't have any points, so this is going to be true. A point is convex, right? Just 1 point. Again, because there's only one element, so x and y have to be the same. And a line is definitely convex. You can check that just because a line has this property being true for any value of t, not just t between 0 and 1. Any real value of t has that property for a line. Here's some more or less trivial ones. So then a norm ball is convex. So if you give me any norm, which I'm just going to note by these 2 double bars, and you give me any constant r, then the set of all x for which that norm is less than or equal to r is a convex set. That r is called the radius of the ball. So we'll talk about norms, I guess, later in the lecture. We'll give you examples of norms, but you should be familiar with norms from basic real analysis, right? Like the Euclidean norm or the L2 norm, the L1 norm, which is the sum of the absolute values. We'll talk about matrix norms a lot in this class. So you'll see examples of norms, but if you're rusty, just go brush up on some basic real analysis. A hyperplane is convex. That's a set of all x for which A transpose x is equal to B for a given constant A and B. Okay, so that, right, if x is in R2, for example, then a hyperplane just looks like this, right? It's a line. And if x is in Rn, then a hyperplane is an n-1 dimensional subspace that has the property that A transpose x is equal to B for some constants A and x, or A and B, excuse me. A half space is convex, so that's the same. It's this same starting form as a hyperplane, except we relax the equality to an inequality. So here that might look like this, right? So this might, in this case, in R2, the vector A would be defined as the normal to this, right? And this might be the the constant half space, the set of all x for which A transpose x is equal to B. So just a line. Oops. Sorry about that. And then down here, this is the half space set of all x for which A transpose x is less than or equal to B. Okay, so this all stuff should all be familiar. Just we're just de-rusting in case you've forgotten. An affine space is a similar concept, except for just instead of just a single linear equality, we have a set of linear equalities. So I'm saying A times x is equal to B for a matrix A, right? And so each row of A gives me a linear equality, right? So if I had rows AI, then this set would be the set of all x for which AI transpose x is equal to BI for all I. Also convex. So you can just check directly from the definition that each of these sets is convex. That's very straightforward. Here's a little bit more sophisticated. A polyhedron is a convex set. So again, now we're looking at multiple sets of constraints. We just looked at multiple sets of equality constraints. Here are multiple sets of inequality constraints. So this looks like AI transpose x is less than or equal to BI if AI are the rows of A. And this inequality, we'll do this throughout the semester, is interpreted component-wise. So if I ever have a vector less than or equal to another vector, like in this case, I mean component-wise inequality. So pictorially, that looks like this, right? Each of these, like I said, each row of A defines a half space. This is the intersection of all those half spaces. This has to be true for every row. So, right, if I intersect half spaces defined by the normals of all these vectors, I get some polyhedron P there. So we can also write a polyhedron, by the way, as a set of all x for which AX is equal to B and CX is equal to D, where C is another matrix and D is another vector. So why is that true? It's just because I can just write this as the inequality that CX is less than or equal to D, and CX is bigger than or equal to D, right? And I can write CX is bigger than or equal to D as minus CX is less than or equal to minus D, and so I can always think of that as, again, I'm just adding more linear inequality constraints, less than or equal to constraints. I can just stack A, C, and minus C into one big matrix, and it's just one big matrix times x is less than or equal to one big vector. A simplex is a very special case of a polyhedron. So it's given by taking the convex combination of a bunch of points. And those points we usually think of as affinely independent. So that's the way we usually represent a simplex, although I can take a convex combination of any finite number of points and it's still a simplex. So what does it mean for points to be affinely independent? Well, what does it mean for points to be, just to remind you, and again, this might be just terminology you haven't heard of. If I have points x0 through xk, and I claim that they're affinely independent, another way of saying that is that x1 minus x0, x2 minus x0, all the way through xk minus x0 are linearly independent. So it's just a different concept than linear independence, but it's important to know that distinction. Right, so let's just come up with an example in R2. So Okay, so let's just do this first of all. Yeah. Are these 3 points affinely independent? No?
Is that R3?
Sorry. Yeah, this is supposed to be R3.
It's hard to tell where they are.
Okay, well that's why I tried to, let's just forget about that. Let's make this R2. No, they're not, right? So why is that the case? It's because if you can think about it this way, if I look at the line segment formed by any 2 points, it contains a third point. So that means that they can't be affinely independent. And you can check that exactly corresponds to this definition. So in general, if I have a bunch of points and I look at the affine subspace generated by like a subset of them, if that contains some of the other points, then they can't be affinely independent. Okay? So simplex, like I said, is a special case of a polyhedron. The canonical example of the simplex is the probability simplex, where we just take the convex combinations, all convex combinations of the canonical bases vectors. So these are the guys that have 1 and 1 component and 0 and all the rest. And that looks like the set of all, say, vectors W that are non-negative and sum to 1. That's a very kind of common one you'll study a lot in optimization problems. It's called the probability simplex. Okay, polyhedra are actually extremely interesting. We're not going to talk about them in too much detail in this course, but one could teach an entire course on polyhedra. They have a lot of very interesting properties. We'll revisit them a bit when we talk about duality, because we'll see that there's another way to represent a polyhedron. So one way to represent a polyhedron is called the half-space representation, which means that I can take a bunch of half-spaces, intersect them, and that gives me a polyhedron. That's a really useful representation for some reasons. So in some instances, we actually want to know this representation. Like if you tell me I have a polyhedron, and then you tell me that it's of the form Ax is less than or equal to B, knowing what A is and knowing what B is can actually be very helpful to me. Another way to represent a polyhedron is to take just a convex combination of its vertices. Sorry, the convex hull of its vertices. So in this drawing, these are its vertices. That's called its vertex representation. So there's a kind of famous theorem in polyhedral theory that says that any polyhedron or any set that's written as a half space, an intersection of half spaces, can also be written as a convex hull of some finite number of points, which are the vertices, and vice versa. So those two things are equivalent. Depending on how much we actually get through in duality, we might actually prove that. It's a kind of very fundamental fact about polyhedra. And like I said, in some instances, one representation is a lot more useful than the other. So it's good to know that they're both possible. In general, it's not easy to know one representation just if you know the other. Right? If I told you that my polyhedron looked like this, Ax less than or equal to B, it's not easy to find its vertices, and vice versa. But we know that at least it is possible to represent it that way. So that was just a bit of a tangent on polyhedra, but I think they're pretty important, so it's good to know about them. Cones. So cones are another kind of fundamental set, and we're particularly interested in convex cones. A cone just has the property that if I take any scalar multiple of a point in the set that's positive, so if x is in the set, I look at a scalar multiple tx of that point, then that's also in the set. And I just restrict t to being positive. So a convex cone, not surprisingly, is a cone that's also convex. So that means that I can take any 2 points and any 2 positive multiples of those points, and it still must lie in the set. Was there a question?
Yes. Is a convex hull a polyhedron?
So a convex hull of a finite number of points is always a polyhedron.
Okay, but you could have an infinite number of points.
Right. So if I have what's the convex hull of a set, right? It's the convex combination of all elements of the set. So what's the convex hull of, say, a circle or a sphere in higher dimensions, right? It's the sphere of the circle. All right, so going back to cones real quick. Okay, a convex cone is a cone that's also convex. Put those two words together, put the two definitions together, that's literally what it means. So you can check that this is the appropriate condition in that case. And it looks like this, right? If I have any 2 points, x1 and x2, then I must know that if I take any positive multiple of x1 and x2, that's still contained in the set. So this gray shaded region is supposed to be a cone here. We can also take a conic combination of points, so it's kind of analogous to the convex combination of points terminology, except for the weights, we only restrict them to be positive. So we don't have to have them to sum to 1. And analogous to the convex combination, if I take a conic hull of a set, which I guess we don't really have consistent notation for, but I may as well just make it up. Maybe we'll just write it like that. We won't actually look at conic hulls that often, but it probably will look like that. Then that's the conic combinations of all points in the set. And just like the convex hull was convex for any set, the conic hull of any set of points is always a cone. Okay? Okay, so what are some examples of convex cones? Remember, these are actually convex sets, obviously, but they're just more special. They're actually cones. So a norm cone is always a convex cone. So I look at the set of all pairs, x and t, where x is a vector and t is a scalar, such that the norm of x is less than or equal to t for some norm, then that's always a convex cone. So what does that look like for the L2 norm? Let's see if we can try to draw it. This is supposed to be R3 now, not to trick you guys. So let's suppose I try to look at the, we call it the second order cone, which is the set of all x, comma t, such that the L2 norm of x, or just the standard Euclidean norm, is less than or equal to t. So what does that look like? So it looks like an ice cream cone. And you guys can verify that this is correct. So I'm just drawing the circle to emphasize that all these points are in the cone, but it extends out this way forever. Right? This is supposed to be t, by the way, and this is supposed to be, say, x1 and x2. So if I look at the L2 norm of x1 and x2 at any slice, so take a slice t here, slice through this convex cone, I have to have the points in that set have to satisfy that the L2 norm of x is less than or equal to that particular value of t. That defines a circle, right, or a ball. So as I increase t, I just get these kind of overlapping, or these adjacent balls, and it forms the second order cone. A normal cone is something different. That's different than a norm cone, even though the names sound the same. A normal cone is associated with a set C and a point in that set. And we'll see this is actually very important. We'll revisit this a bunch of times. If you give me any set, and so here I drew a set that looked like this, and you give me some point on the set, so first let's look at, say, this point, x, then the normal cone, as you can see according to this definition, it's the set of all points that maximize the inner product with respect to some vector, with respect to the given x among all points in the set. So said differently, right, I want to have the normal cone of this set C at the point x is the set of all vectors g such that g transpose x is equal to the maximum over all y in the set C of g transpose y. So if I look at the inner products of vectors with the given point x, they have to be maximized at x versus all other points in the set. So what does the normal cone look like for this point x here? This is 0. So I want to look at all vectors g whose inner product with x is bigger than anything else, than the inner product with anything else in the set. Right here, okay. So here's 0. Here's x. Right. I want to look at vectors that have maximal inner product with x over all other points in the set.
Should be the extension of this one.
What's that?
The extension of this one.
Okay, so what happens if I extended that line? Can I find any vectors that have a bigger inner product with x? Which ones are they? Sorry, what happens if I chose that to be x and g was this guy here? Does any guy have a bigger inner product with g than x does? How about this vector here, y? Whose inner product with x is bigger? With g is bigger, x or y? Y's is, right? So that's not it. So it can't just be extending that out. Any other ideas? It's drawn on the picture. I'll give you guys a hint. The reason it's called the normal cone is because you can think about it as a normal vector to the surface of the set. So I'll just move this over so I have more room to draw. This is the normal cone of C at x. Right? This should make a right angle in a sense with the boundary of the set. And I'm actually drawing, just to be perfectly precise, I'm translating the normal cone so that it starts at the point x. The normal cone is actually defined just as a set of vectors, right? So it's actually all these vectors here at the origin. But I'm just drawing it so that you can see it more clearly by translating this normal cone up to start at the point x. So now you can check that actually x has maximal inner product with any vectors that lie, g that lie on this line, or on that half line, which is a cone. Okay, so make sure that makes sense to you. Draw a few more examples, and then you can also quiz yourself after class that the normal cone at this point in this set is actually it's bigger in some sense because it has a higher dimension than the normal cone at this point, and it looks like something like this.
C has to be convex, correct?
Good question. So the normal cone is always defined, regardless of whether C is convex or not. The kind of amazing property is that it's also always convex, even if C is not convex. And that you can check directly from the definition.
Does x has to be lying on the boundary?
No, x has to be in the set. That's it. So let's try something else. What happens if x is in the relative interior of the set? So what happens if that's x? What's the normal cone of the set at x? C at x? Just 0, right? It's not empty because 0 is always in a cone, but yeah, it only contains 0. So if the point's in the relative interior of the set, then the normal cone is kind of trivial. So we'll see that this has really nice connections to a bunch of things that we learn, like subgradients. In fact, it may reappear even in the next lecture. So it's a good thing to know. All right, now moving to the matrix world, we're going to talk about the positive semi-definite cone. So whenever we move from vectors to matrices, I think some students are always confused by this transition because it seems like all of our definitions were somehow special to vectors, and now we're talking about matrices, so they get confused. But think about a matrix as just taking a vector and unraveling it to be something of a higher dimension, right? So an m by n matrix you can think about as a vector of length m times n. Just do some way of consistently unraveling it, like do it in column-wise order or something. Then think of that as a vector and apply all the definitions you know to vectors to that particular object. That's going to give you all the definitions you need for matrices. Okay, so that's the most rigorous way to think about it. That's probably not the most efficient way to think about it because maybe you'll spend too much time double checking that your intuition is right. The best way is just to follow your intuition. Mostly all the kind of corresponding operations for matrices are just exactly what they would be for vectors if you unraveled them. So just follow it that way. And if you're ever unsure, you can think about kind of this more rigorous way of unraveling it. Okay, so now we have definitions for matrices for convexity, just from that property I described. So don't be too confused by them. And we're going to talk about the positive semi-definite cone, which is a set that's defined over matrices. I'm going to use this script Sn, kind of analogous like I do for the set script Rn. I'm not sure that's the script, whatever that's called, math blackboard font or something in LaTeX, to be the set of all n by n symmetric matrices. Okay, and if I look at the matrices within this set of symmetric matrices that are positive semi-definite, which I'm going to write as Sn lower script plus, then that forms a convex cone. So in this particular case, actually, I don't have to think about unraveling every element of the matrix X, just like, for example, its upper diagonal, right? Because this is actually a vector space of dimension n times n plus 1 over 2 rather than n squared, because the lower half of the matrix is redundant, right, once I know the upper half, for a symmetric matrix. So in this case, if you want to know what it meant for symmetric matrices to be convex, all this stuff, think about that unraveling. So what does positive semi-definite mean? Just to remind you, it means that if I take, right, X is positive semi-definite, which we're going to write as this kind of curly bigger than or equal to 0, it means that A transpose XA is positive for any A. It also means that the smallest eigenvalue of X is non-negative, bigger than or equal to 0. Okay, so if that is rusty, then go look up some of your linear algebra notes. What are some key properties of convex sets? Well, there's really only 2 of them. Admittedly, we're not going to use them that much, so I'm not going to spend much time on them. They're actually important to prove a bunch of the stuff that we're going to just kind of take for granted. So these are fundamental at that level, but we're not really going to use them so much. So we'll just go through them quickly. There's the separating hyperplane theorem, which tells us that if we have any 2 disjoint convex sets, C and D, then there's always a separating hyperplane between them. So a little more formally, right, if we have any 2 convex sets that are non-empty and that are separate, so they don't, they have a trivial intersection, then I can always find some vector A and scalar B such that C is contained in the half space A transpose X less than or equal to B, and D is contained in the half space A transpose X is bigger than or equal to B. So there's the picture. So that's a pretty fundamental property. Here's a question. What about strict separation? Can I always have, if C and D have the property, right, that C and D are non-empty, and they don't intersect, what about strict separation? So can I find some A such that C is contained in the set of all X such that A transpose X is less than or equal to B, and D is contained in the set of all X such that A transpose X is bigger than B? Is that always possible?
No.
It's not possible. What's an example where it's not possible?
You just have to draw non-linearly separable sets. Something that curves around.
Yeah, but I mean, these were not linear. These sets were not polyhedra.
Non-convex, right?
Oh, okay. Convex. Sorry. I was assuming that was implicit.
They're just very close.
Yeah, very, very close. I mean, that's kind of what we want. But, I guess you can think about if the sets aren't bounded, it makes it kind of easier, right? So let's suppose I'm in R2, and one of my sets is just everything whose y coordinate is negative, so that's D. And my other set C is what we'll learn very soon as the epigraph of the function y equals 1 over x squared. Right, so that's C. Right, so they are convex. They don't intersect. They're not empty. But I cannot find a separating hyperplane a strictly separating hyperplane between the 2 of them, right? Because the points in the epigraph of this set C, the points in C, let's just say, forget about epigraph. We'll learn that in a few minutes. They get arbitrarily close to the x-axis. So you can't always have strict separation, but you can under some conditions. Yeah.
So would that mean that they have to have non-empty intersecting boundaries?
In this case, they do. Yeah. The other one is the supporting hyperplane theorem, similar in a sense, which says that if you have a convex set and you take a boundary point, then it has a supporting hyperplane passing through it. And that is a supporting hyperplane is defined by a vector A, normal vector A, and it has suppose the boundary point I'm calling x0, it has the property that the set of all x for which A transpose x is less than or equal to A transpose x0 contains the set C. Okay, so C is contained in this particular half space that's defined to be passing through x0. So both of these theorems have partial converses, which is a kind of amazing property of convex sets, which means that if you have something like a set such that every boundary point does have a supporting hyperplane, then under a little bit more conditions, that set has to be convex. And the same thing with the separating hyperplane theorem. So there are kind of partial converses. You can see the section 2.5 of your Boyd and Vandenberg supplementary textbook for that. So here's the good stuff. Operations preserving convexity. And let's see, how many do we have of them? We have 6, or 5. There's more. You can read some of the supplementary materials that we put on the website. Some of the supplementary textbooks that we list at the end of this document. But here are the 5 main ones. The intersection of any two sets is convex. Falls right from the definition. In fact, all of these you can check from the definition, so we're not going to prove them. But they're very handy. Scaling and translation. So if I take any convex set C and I multiply it by a constant A, and I add to it a vector B, then that set is convex. Right? So we're going to write that as AC plus B. So the set of all AX plus B, where X is in the set. That's a special case of actually the following, which is taking affine transformations of the set, or an affine image of the set. So if I take any affine function, which looks like a matrix A times X plus B, and a convex set, then the image of C under the function f, which you write as f of C, the set of all f of x for which x is in the set C, is convex. And if D is a convex set, then the affine inverse image, or the pre-image, is also convex. So this is actually extremely important to know, these two, because I feel like affine transformations happen all the time, and it's super handy to know this fact. It's also important not to confuse this with the inverse of a function. So it's maybe a slight bit of unfortunate notation, because f does not need to be invertible for this affine preimage to exist. Look, it's just the set of all points x for which f of x is in D. So there's nothing to do with its inverse here. Okay, so a lot of times we'll look at affine transformations that aren't invertible, and we'll still talk about the affine preimage. Okay, so it's just notation. So here's 2 things you can prove right away with these operations that preserve convexity. We'll go through both of them. The first is that if I have anything we call a linear matrix inequality, then that's a convex set. So if you give me matrices A1 through, I guess I called it AN, that's supposed to say AK, another typo, sorry. And another matrix B, which these are symmetric matrices. Then the set of all x such that x1 A1 plus xk AK being less than or equal to B. And remember, this actually means that B minus all these matrices, minus this sum of matrices. So this means a scalar x1 times the matrix A. So I'm just scaling every element of A1 by the amount x1. So B minus this matrix is positive semi-definite. That's what that means. Okay, so just to be super clear, that's what we mean by this notation. B minus x1 A1 plus xk AK is positive semi-definite. So that's going to be convex. That's a convex set in X. And that's true for any matrices A1 through AK and matrix B. So these don't have to be, for example, positive semi-definite to begin with. All right, so how do we prove that? There's 2 approaches. The first is to check the definition. Right, we have to check that any convex combination of points in the set, say just for 2 points, still lies in the set. So let's just do that. If I take I'm not sure why I wrote down only this for 1 here. I should have written this down for 2, so that there's a bit of a typo there on the slide. Let's suppose I take, oh no, I did this right, sorry. So let's suppose I have a point x and a point y both in the set, right? That means that they both satisfy this. So if I take the linear combination of a's with the x points or with the y points, they both are less than or equal to b in the matrix sense. So now I want to prove that tx plus 1 minus ty is in the set. So I have to check that this inequality is still true, right? For if I take these leading weights on the matrices A. That means that actually B minus the sum of txi plus 1 minus tyi times ai, I equals 1 to k, has to be positive semi-definite. That's what we want to show. And remember, that's equivalent to saying V transpose B minus txi plus 1 minus tyi V is bigger than or equal to 0 for all V. Right? So just move this through, right? And you get V transpose B minus, actually, so I'm going to first note that I can write B as TB plus 1 minus TB. Can always do that, right? So I'm going to rewrite this as T times V transpose B minus the sum of xi. I guess I left out an ai here, sorry. ai transpose V. So I just took out the t, and I took out this term and these x points plus 1 minus t times the same thing for the y's, right? V transpose sum of yi ai v, right? That's exactly equal. These things are equal, and each of these terms is bigger than or equal to 0, right? By the definition of this matrix being positive semi-definite by assumption, because x and y are in the set. All right, great. Followed from the definition. Approach 2, much less laborious. We don't have to actually go to the definition. This is why this is not like an example where you save yourself a lot of work, because this was pretty easy, but you'll save yourself a lot of work in the future. We're just going to think about this. What is this set? Well, it's actually just the affine preimage of the positive semi-definite cone. So I'm looking at the set of all matrices that are positive semi-definite. Let me define this function as a function of x just to be b minus the sum of xi ai. It's an affine function. This set, the one I wrote up here, is just exactly the affine preimage of the positive semi-definite cone. Positive semi-definite cone is convex. Affine preimage is preserved convexity. So we're done. Here's another example. And this one is nice because it relates to principal components analysis, which we will talk about next time. How about something called the fantope? So this is a set script F, which is the set of all matrices Z symmetric that have the following property. Z is positive semi-definite, and I minus Z is positive semi-definite. And also the trace of Z is equal to K. So K is some constant that we call the order of the fantope. We might write it as F subscript K. So just so that you're familiar with some of the equivalences that we might write here, what does this mean? This means that all of the eigenvalues of Z, which I'm going to write as lambda 1z through lambda nz, they're between 0 and 1. Right? That's because positive semi-definite means that they all have to be bigger than or equal to 0. And I minus z, positive semi-definite, means they all have to be less than or equal to 1. And what's the trace of a matrix? It's the sum of the diagonal entries of the matrix but we also know from kind of a fundamental property that it's the sum of the eigenvalues. That's another way of expressing the Fantôme. Okay, so that's a nice set. We'll see that it actually relates to principal components analysis in a nice way, an interesting way next time. It's convex again. There's two ways to do it. Approach one, go to the definition. Okay, so we're going to skip that one because we already did that one for the last thing. It just kind of follows from some of the properties of trace and positive semi-definiteness. Approach two, we're just going to recognize the fact that it's the intersection of some convex sets, which we know is convex. So we're going to write this as the set of all vectors z that are positive semi-definite and, sorry, not vectors, matrices z that are positive semi-definite and for which I minus z is positive semi-definite and for which the trace of z is equal to k. So I just kind of use shorthand here, right, for each of these sets. I really should write z in the set of symmetric matrices such that these are true. So each of these is convex. That's the positive semi-definite cone. Why is that convex? I mean, there's many ways you could say it, but this is, for example, an affine transformation of the positive semi-definite cone, right? And this guy is an affine transformation, is a linear equality constraint on z, right? Because trace just sums the diagonal entries. So I can think about it as some matrix which pulls those out times z summed up is equal to k. So it's a linear equality constraint on z. Each of these guys we know is convex. Intersection of convex sets is convex. It's a little bit easier to see that way. Okay, here are some more operations preserving convexity. Then we'll take a break, and then we'll come back to convex functions.
Can you define this operator that looks like greater than or equal than, but like 30?
I'm sorry?
Could you define this operator that looks like the greater than or equal than?
Uh-huh. Sure. So yeah, that was here, in case you forgot. So a matrix is positive semi-definite, which we write with this curly bigger than or equal to if it's positive. So this means positive semi-definite. So it means that A transpose XA is bigger than or equal to 0 for all vectors A. Okay, here are two nice ones. I think we're probably not going to go through the example of this one, just for the sake of time. But go through it on your own. Perspective images and pre-images are also convex. So the perspective function is something that takes two arguments, one a vector and one a scalar. And the scalar has to be strictly positive. That's the domain of its kind of second block of argument. R++, this means positive reals. And it takes the first vector, x, and divides it component-wise by z. And there's a nice interpretation of this in terms of pinhole cameras. I think it's kind of cute, but doesn't really do much for me personally in terms of remembering it, so I'm not going to talk about it. But you can find that in the Boyd and Vandenberg textbook. It turns out that if I have a perspective function, this guy here, and I have a convex set, then the image of that convex set under perspective function P is still convex. And the pre-image of a convex set is still convex. Again, very useful fact. And this one is actually pretty non-obvious, I think. It's certainly less obvious than the affine transformation one. So that gives us some nice transformations that we can also kind of keep in our toolbox. The next one is the linear fractional image and pre-image. So it's the perspective map composed with an affine function. So we know that the perspective map is always convex. What happens if I compose this with an affine function, which means that instead of taking P xy, I take P of an affine transformation of x and y. I can write that affine transformation as x goes to ax plus b. I guess I kept saying y. Excuse me, I meant to say z. And z goes to cx plus d. Okay? And this is, again, the perspective map is only defined when its second argument is positive. So the linear fractional function is only defined when its denominator, cx plus d, is positive. It's the same thing. This is what a linear fractional function looks like. It's it has the same property. It preserves convex sets under its image and also under its preimage. So the linear fractional image of a set is convex if that set is convex, and same with the preimage. Okay, so I think this probably is the least obvious transformation that preserves convexity in terms of images and preimages. But it's really just built up of things we already know, right? Affine transformations and then a perspective function. So we'll see examples of these later. I guess you'll get a better feel for them. Go through this one in detail if you're confused. This is a good one. It shows that if I have kind of a prior set of joint probabilities, and that's convex, then if I take the set of conditional probabilities of one variable given another, that prior set of conditional probabilities is still convex. That just follows from the fact that it's a linear fractional transformation of the original joint probability distribution. So thanks to some of you guys for pointing out that this was a bad example I gave. So I was misleading you guys here. This is an example where strict separation does seem to hold, right? Because if I just take the set of all points for which the x-coordinate is strictly or is less than or equal to 0 versus the set of x points for which the x-coordinate is strictly bigger than 0, then that does strictly separate these two, right? Because this will never actually touch that hyperplane. So that was a bad example. But it's not always true we can get strict separation. And I'll leave it up to you to try to think of a counterexample. You have an example you want to share?
Well, you can think of two half spaces where one is closed and one is open. Or like the complement. You can think of a half space and its complement.
Yeah, but they intersect.
Well, the complement. One is open, one is closed.
Uh-huh. But then by definition, they're strictly separated, right?
All right. Wait. No, they're not. Because if you think of the hyperplane, it's contained in one of them, right? Oh yeah, yeah.
Yeah. So, I mean, there are examples that I think probably are not too hard, but it's not worth our time spinning our wheels now. But yeah, you can look that up. Strict separation is not always true. Check out chapter 2.5 or something like that, of Boyd and Vandenberg. So let's get to functions. Functions, in a sense, like I said, are kind of more important, but kind of everything that we know about functions comes from what we know about sets. So since we knew sets really well, we can always derive things for functions. So we're not going to spend quite as long on them, but they're very important. A convex function, you already know, is one for which the line segment joining any 2 points in the graph of the function lies above the function. So that's this picture, right? F of tx plus 1 minus ty is always less than or equal to tf of x plus 1 minus tf of y for all t between 0 and 1. Concave function just means that the reverse is true. So I get the reverse inequality here. The easiest way to think about it is actually that f is concave if and only if minus f is convex. So everything we talk about for convex functions has an equivalent definition for concave functions. Just define it according to minus f. Some important modifiers are strict and strong convexity. And these come up a lot, especially when we talk about kind of convergence properties of algorithms. And your first homework is going to have you prove some equivalences for strongly convex functions, some more characterizations for them. What do they mean? Strict convexity means that we get a strict inequality. F of tx plus 1 minus ty is strictly less than tf of x plus 1 minus ty, as long as t is between 0 and 1 and x and y aren't equal. So it's just this picture. The line segment joining x and y is strictly above the function inside that interval. Strongly convex means that I can subtract off a quadratic function. So here I'm writing as some constant m over 2 times the norm of x squared. So this is just the sum of the squared components of x. And that's still convex. So if I can do that for a function f, it's called strongly convex, and m is called its strong convexity parameter. So just remember, in words, you know what convexity means. Strict convexity means it's more convex than a line. Right? It has more curvature than a line. Strongly convex means it's more convex than some quadratic. And that quadratic is going to have the parameter m governs kind of how curved that quadratic is. Okay, so you can check that strong convexity implies strict convexity, which in turn implies convexity. So strong convexity is the strongest form of convexity, and then strict convexity, and then convexity. Okay, so the analogous definitions hold for concave functions. Just plug in minus f, and we'll get a lot more feel for them as we go on.
So if you prove strong convexity for any value of m, it's strong. So there's no parameter for this string.
Sorry?
Can you say that could a function be strongly convex when m is equal to half, but not when m is equal to 1?
Yes. So m is the strong convexity parameter for the function. So yeah, it's paired with the property of being strongly convex. So we'll say like a function is m strongly convex. What are some examples of convex functions? A bunch of univariate examples, right? We'll just draw them real quick. Exponential function is convex for any a in the exponent, constant a in the exponent. Power function is convex, so I'm not a great artist, but I know it goes up less slowly. It goes up slower than the exponential function. That's convex if a is bigger than or equal to 1, or if a is less than or equal to 0, right? If a is less than or equal to 0, it looks something like this. Not if a is in between 0 or 1, strictly. Because then it's concave, right? So like, for example, the square root of x looks like this. And the logarithmic function is also concave. Great. So those are some easy univariate ones. Affine functions are both convex and concave. You can check the definition is satisfied because they get equality here, right? So it's true if I put less than or equal to or bigger than or equal to. Quadratic functions are convex provided that the quadratic form q is positive semi-definite. So a quadratic function looks like, the half is just for convenience, 1/2 x transpose qx plus b transpose x plus c. As long as q is positive semi-definite, that's a convex function. And the least squares loss is always convex in, say, x. So this is important to know because we use least squares all the time. Why is that? It's because this is just a quadratic function. So this is right equal to x transpose ax minus 2 for example, y transpose ax plus a constant. And look, this is a quadratic function. What do we need for a quadratic function to be convex? We need for its quadratic form to be positive semi-definite. A transpose A is always positive semi-definite for any matrix A. So least squares loss, always convex, no matter what that matrix A is. Norms are convex. Super helpful because we use norms all the time too. If you forgot about what a norm is, like I said, go back to some of the summary or some of the prereq materials that we put up on the website. We're going to use LP norms a lot in this class, and we're going to use matrix norms a lot in this class. LP norms are norms whenever p is bigger than or equal to 1. So we call something like the L0 norm, for example. That's really a misnomer. It's not actually a norm. It's just what we call it. So any norm is convex. That's the fact. And think about LP norms for p bigger than or equal to 1. So it's defined as follows, right? The p norm of x is just the sum of the pth powers of the components of x, that whole thing to the power of 1 over p. And we use the infinity notation to denote the maximum absolute component of x. Use these guys a lot. Matrix norms we'll use a lot also. The spectral norm and the nuclear norm, also called the operator and trace norms. So I don't really know which one I'll use, like in terms of nomenclature. I guess I might mix them up throughout the semester, but operator and spectral both mean this guy, the largest singular value of a matrix, and trace and nuclear both mean this guy, the sum of the singular values of a matrix. Okay, these guys are both norms. How about some more functions? Indicator function is always convex. So the indicator function we're going to write as I sub c of x, and that's going to be 0 when the point's in the set, and infinity when it's not. That's always a convex set, provided that c is a That's always a convex function, provided that C is a convex set. The support function of a set is convex. And that's true whether or not C is convex. It's a very nice property. And I wrote it as I star of C for a reason that may look mysterious, but we're going to see when we talk about duality that there's a good reason to do that. So the support function is defined as the maximal inner product with the point x over all points y in some set. So the support function of C at a point x is the maximum value of y transpose x for all y in the set. That's always a convex function, even if C was non-convex. The max function is always convex, another important one to know. If I take the maximum of, say, the components of some vector x, it's a convex function. So here are some key properties of convex functions. And I think for these are, I'd say for convex functions, operations that preserve convexity and properties are kind of equally important. There wasn't really, the properties for convex sets, like the supporting hyperplane and separating hyperplane, weren't as important in the sense we won't use them as much. But the properties we'll use a lot for functions. A function is convex if and only if its restriction to any line is convex. That's a very important one to know. So if I have a function that's from Rn to R, and I look at a line in Rn, and I actually look at how the function behaves over that line, if that's convex no matter what line I take in Rn, then that's true if and only if the function itself is convex. Here's the one that connects functions to sets in terms of convexity. A function is convex if and only its epigraph is a convex set. So just to draw you a picture, we already had an example before, but you didn't know what an epigraph was then. The epigraph is a set of all pairs x and t that are in the domain of the function and R. T is in R, x is in the domain of the function, such that f of x is less than or equal to t. Right? So if this is the function f of x down here, it's a set of all points for which t is bigger than what happens when I evaluate the function. So this function is convex if and only if this set is convex. So a very important property connecting sets and functions. In fact, once you knew that, you could derive everything about convex functions from sets. And we really only deal with convex functions for convenience. I know it sounds silly, but everything we talk about in the class, including very complicated things like the KKT conditions and so on and so forth, they could be all derived from convex sets, just knowing this one fact. Sublevel sets. So if a function is convex, then its sublevel sets are convex. That's a little bit similar to the epigraph, but t is not, t is fixed here. We just take one t and we talk about its sublevel set at some t. It's a set of all x in the domain such that f of x is less than or equal to t. So for example, if I take t to be this value, the sublevel set is a set of all x for which f of x is less than or equal to t. It's going to be all these points. Right? So if a function is convex, then all of its sublevel sets are convex, no matter what t is. I claim the converse is not true. And for that, you can see some easy examples, right? Suppose this is my function, not convex, but all of its sublevel sets are convex. But if I take any t, and I look at the set of all x for which f of x is less than or equal to t, they're all convex sets. What do I call a function that has convex sublevel sets, but it's more broad than just a convex function? A function that has convex sublevel sets is called quasi-convex. And we're not really going to talk about those types of functions, but it turns out you can say some stuff about them also. Okay, here are the important properties of convex functions. The first two are really the most important part. There's a first order characterization and a second order characterization of convex functions. If f is a differentiable function, then it's convex if and only if it has the property that for any points x and y, f of y is bigger than or equal to f of x plus the gradient of f of x transpose y minus x. So in words, the tangent to the function at x is an under approximator for the function. Right? The function lies above its tangent line. This is also sometimes called its first order Taylor expansion. Okay, so just to draw a picture, right? Convex function, here's x, here's the tangent line. the function has to lie above its tangent line everywhere. The tangent line is defined by this over all points y. So therefore, we can immediately see that if you have a differentiable convex function and its gradient is 0 at a point x, then x minimizes the function. Right? If its gradient is 0, then this term is 0. And it tells us that for all y, f of y is bigger than or equal to f of x. It's like our first optimality condition for convex functions, differentiable convex functions. That one I think you knew already, I'm sure. Second order characterization is, has to do with the Hessian of a function. If f is twice differentiable, so it has a Hessian exists, it's Hessian matrix, then it's convex if and only if the Hessian is positive semi-definite for all x. So remember, the Hessian is a matrix, whereas the gradient is a vector. Again, review this stuff if you've forgotten. And it's the extension of what you knew from univariate calculus, which says that if the second derivative is positive, then the function is convex. This is just saying that for multiple inputs, multiple variables. So we have to have the Hessian positive semi-definite for all x in order for the function to be convex. So we'll use these a lot. Jensen's inequality is one that you see quite often also. I'm not going to really spend much time on it because I'm sure you've seen other courses. But if f is a convex function and x is a random variable, then f of the expected value of x is less than or equal to the expected value of f of x. In some sense, this is actually just the extension of the definition of a convex function, right? Because we know this is true for a random variable that is supported at 2 points, x and y. Some operations preserving convexity. Here are 3. Any non-negative linear combination of functions is convex. Why do we have to have the weights being non-negative? It's because if we had these being negative, for example, then we could make one of these functions concave, right? If I took them all to be negative, for example, it will be concave if these are all convex. Pointwise maximums and pointwise and minimums are convex under some conditions for the minimization and under no conditions for the maximization. So that is, if I have a bunch of functions which are indexed by s, and each of these is a convex function for each index s, then the maximum of all these functions at a point x is a convex function of x. Okay, so this can be true even if the set S contains infinitely many functions here. You can check this directly from the definition. So this is nice. It's very useful. It's an extension of that property that the maximum of x1 through xn is a convex function. This is actually true no matter what you're taking the maximum of, as long as those things are individually convex functions. Partial minimization is also convex. I called it pointwise minimization, but that's really not as accurate as a descriptor. If I have a function that's convex in x and y, jointly in 2 variables, and C is a convex set, then if I minimize out overall y in some set C, that function that remains as a function of x is still a convex set. It's still a convex function, excuse me. Okay, so this is only true if the set C is convex. So here's an example to get you to put those in mind. Let's consider maximum and minimum distances to some set C. And you'll see that one of these is always convex, the other is kind of only convex when the set C is convex. So let's suppose I have a set C and an arbitrary norm that I write like this. And now I can draw it like this. It doesn't need to be convex. And I have a point that I write as x. And I want to look at the maximum distance between x and the set C with respect to the norm, this norm. So if this was Euclidean norm, I'd be looking for, I don't know, probably something like this point, right? I'm looking for this distance, actually, the distance between x and y. The maximum distance between x and the set. So that function is always convex, no matter what this, whether the set is convex or not. That comes from the pointwise maximization rule, right? Because this is a convex function of x minus y, no matter what y is. We're maximizing out over all points y, so what remains is a convex function. It's the partial. That's the pointwise maximization rule. How about the minimum distance to C? So if instead I'm looking for the closest point to x, and I'm measuring that distance, that's not always convex. But it is convex when the set C is convex, from the partial minimization rule. Okay, again, this is convex in x and y jointly. It's an affine function. If the set C is convex, I can minimize out over y. Okay, so we're almost out of time. We actually don't have much left. So I'm just going to go through the more operations preserving convexity. There's really only a couple more, and then we'll quit. So this one you'll use a lot. Just like I said, you'll use a lot for convex sets. Affine composition is something that happens all the time. You have a convex function. Instead of applying it to kind of x, you'll apply it to ax plus b, where a and b are constant matrix into some constant vector. As long as the original function was convex, this new function is convex as well. This is really useful when you want to prove something's convex and you recognize an affine transformation in there, because affine transformations mess up sometimes things like taking gradients and Hessians. They don't mess them up in the sense that they're incalculable, it just makes it more complicated. So don't bother with that. Just do it for the case where there's no affine transformation, and then claim that, when the affine transformation is in there, I'll still have convexity. General composition is a lot more restricted. We can't just compose convex functions and get a convex function. And unfortunately, the rules I don't think are super easy to remember, but I've listed them here. You can come back to them when you want to check that you have a convex function. Let's first suppose that I have a function g that goes from R into R, and then a function h that goes from R to R. And I compose those two to get f. So f of x is equal to h of g of x. Then there's a bunch of rules for when f will be convex depending on what happens with h and g. I'll read the first two to you. F is convex provided that h is convex. So this outer thing is convex. G is convex. And, this is the key property, h is non-decreasing. So it's increasing, but maybe not strictly so. If that's the case, then that's f is convex. Another one is that if h is convex, and g is concave, and h is non-increasing, so it means that it's decreasing, maybe not strictly so, then f is convex, which you could have guessed, right? Because I can consider that the same case as the first one, just with taking minus g instead of g. So how to remember these? Think of the chain rule. That's probably the easiest way to remember them when n equals 1. If you take the chain rule, take two derivatives of f, you get h prime of g of x times g prime of x squared plus h prime of g of x plus g double prime of x. And now let's look at, for example, this second rule. If h is convex, this is always positive. This is always positive regardless of what g is. So this term's always positive. Now if g is concave, then g double prime is negative. And if h is decreasing, then h prime is negative. So I multiply two negative things together and I get a positive. So I get positive plus positive, which means that f double prime is positive, which means that f was convex. So if you didn't remember the rules, you could have thought of the chain rule and kind of re-derived them. But here are the rules. They all kind of follow from this intuition, but they apply regardless of whether or not the functions h and g are convex. Vector composition is the same thing, you just do it component-wise. So I'm not going to go through that. So that's it. You've learned essentially all the operations that preserve convexity for sets and functions, all their examples and properties. Maybe at the start of next lecture, you guys will go through this example if you find it helpful. One very last thing. Sorry, we're kind of pushed right against the end. Next Monday is MLK Day, so there's no class, so don't show up. Unless you want to, I won't be here. Next Wednesday, unfortunately, I'm traveling, but one of your excellent TAs is going to cover the course then. So, all right, we'll see you guys soon.